Okay, we're going to look at cooling curves in this video, which are a lot like heating curves. So if heating curves have made sense, then these will probably make sense too. The only difference is we take this and we flip it over, and we kind of mirror it on the other side. Okay, it's going to be like the reverse or the opposite of whatever we did over here. So in a heating curve, we started with a solid, okay, that we heated up more and more and more until we changed it into a liquid. Okay, that process is called melting. It's a phase change, and specifically, it's an endothermic phase change, something that has to take heat in. We're absorbing. Endothermic means heat in. Once we have changed all of the solid into a liquid through that melting process, which happens at the melting point, in the case of water, 0 degrees Celsius, we can continue to raise the temperature of the liquid until we reach another phase change, another endothermic phase change, we call boiling, where we change our liquid into a gas. Okay? Once we get through that process, we have just a gas left. We can continue to increase the temperature of that as we go. Anytime we are changing the temperature of something, okay, that is due to the particle's kinetic energy. Okay? The average kinetic energy of the particles down on that itty-bitty atomic level moving around, okay, is what gives us temperature. Okay? The way that they move and bounce and hit things is basically temperature for us. So we're measuring temperature here in degrees Celsius, but for particles, we think of their temperature as kinetic energy, how fast they are moving. Okay? Now, in the case of a cooling curve, rather than putting heat in, we're going to be taking heat out. We're going to be removing heat. And specifically, we're going to do it at a constant rate. So my x-axis is going to be time in minutes. As we remove heat. Okay? And we're going to start where we left off from the heating curve. Okay? At the end of the heating curve, we had a hot gas, okay, with a lot of kinetic energy. We're going to start with that and start to decrease the kinetic energy of that gas by removing some heat, again, at a constant rate. So over this whole time, we're going to keep it pretty consistent. So as we would expect, the temperature drops. Right? We're removing heat from it. Our particles start to move slower and slower, which means they are a lower temperature. Okay? This is, again, because they're losing kinetic energy. I got kinetic energy abbreviated as Ke here. Okay? Now, at some point, which happens to be what we call the boiling point, our kinetic energy drops so low that our particles start to come back together. Okay? These gas particles start moving so slow that they start attracting to each other. And they start kind of squeezing back in near each other. So as they lose more and more energy, okay, our temperature stops dropping for a while, and instead, the energy that we're losing comes from potential energy. Okay, as those particles attract each other and stick together, okay, the spacing decreases between particles. Change to purple. Potential energy is going to be PE. All right. So as we get those particles closer and closer together, what we're doing is forming the liquid. So what we have here is the gas and the liquid together at the same time through this process where we're changing the gas into the liquid throughout this kind of stretch of flatlining, where temperature is not changing. Okay. This change, this phase change from a gas to a liquid, has a specific name. Okay. It's basically the opposite of boiling. Instead of calling it boiling, we call it condensation. So we are condensing our gas back into a liquid. We're putting all those particles back near each other. Okay? Well, when we had the liquid and gas before, okay, when we were boiling, that was an equilibrium between those two phases of matter. It's the same two phases of matter here, just going the other direction. So we should have an equilibrium here too. All right, so during condensation, the gas and the liquid phase, okay, should be in equilibrium. All right. Now, again, this temperature for water is 100 degrees Celsius, which we call the boiling point from the other direction. Now, it's not really any different. Okay, this is still technically the boiling point, even though we're not boiling it. But this bothers some people because it's like, well, I'm not boiling it, I want to give it a different name. So we can call it something different. Fittingly, since we are going through condensation at this temperature in the other direction, we can call this the condensation point. The only difference between the condensation point and the boiling point is, in this case, we are removing heat instead of adding it. So you could say it happens at the boiling point. You could say that boiling happens at the condensation point. It doesn't really matter. It's the same temperature. It's the direction that we move in based on whether we are adding heat or we are removing heat. Okay. Well, once we have all of our gas condensed back into the liquid, our temperature can start to drop again. Which must mean for this liquid, our kinetic energy is decreasing. Our particles are once again moving slower and slower and slower. Okay? So as long as we've got the liquid alone, that energy that's being lost affects how fast those particles are moving. Okay? Until that is, we reach another point of phase changing at 0 degrees Celsius. Once again, our particles stop moving slower and slower, and instead that lost energy affects how close they are together. They start attracting and getting closer and closer, even more so than they were in the liquid phase. So potential energy is decreasing again. All right. As those particles of the liquid get closer and closer, they're forming a solid. Now we have a word for this too. Okay, this phase change, where we change from a liquid to a solid, is called freezing. Right. Again, freezing happens at the same temperature as melting, just going in the other direction. So we could say this happens at the melting point, but it bothers some people. So we can rename this to be the freezing point since we are going through the process of freezing at this temperature. But it's the same temperature. All right. Just like with melting, we have an equilibrium here. Okay? The solid and the liquid are together over here, and now the liquid and the solid are together over here. In the process of freezing, we are forming an equilibrium between those two phases of matter. So we've got an equilibrium there too. Okay. Now finally, I can continue to drop the temperature of my newly formed solid once all of that liquid has frozen into a solid. And of course, if my temperature is dropping at the particle level, that means my particles are moving slower and slower and slower, which means kinetic energy is decreasing. Okay. Well, we had a specific name for these phase changes for a heating curve, where melting and boiling were both endothermic phase changes. Okay? A cooling curve shows phase changes also, except now we're removing heat, so they should probably get a special name too. Okay? It's still about heat, so we still want thermic to be a part of that, but rather than it being endo for in, we want it to talk about heat going out. We're releasing heat. So this is going to be exothermic. Again, where thermic just means heat. And exo means out. Okay. Which leaves us with a pretty complete picture of how we can change different phases of matter. Let's see if we missed anything. Looks pretty good. Okay, so in a cooling curve, we typically start with a high temperature gas. We continue to remove heat and can therefore change from the gas to the liquid and the liquid to the solid, which we call condensation and freezing. They are both exothermic phase changes. Okay, so we are getting heat out of there and looking at how the kinetic energy and the potential energy change over that time.